Very well. Hello, welcome to today's lecture. We are still on chapter 12. We're done with 12.1, 12.2. We're going to start 12.3. So what we learned so far, we talked about vectors. We talked about vectors in two-dimensional and three-dimensional space. So suppose we have two vectors, V, A, B, C, U, E, F, G, or you can use X sub 1, X sub 2, and Y sub 1, Y sub 2, Z sub 1, Z sub 2. So you can use that format, writing everything in its components, Z sub 1, X2, Y2, and Z2. We learned that we can add and subtract these two vectors and form new objects. So the sum of these vectors is a new vector denoted by V bar plus U bar, which is the sum of the first coordinates, X sub 1 plus X sub 2, Y sub 1 plus Y sub 2, and Z sub 1 plus Z sub 2. With the same discussion, we can define the difference of these vectors. We just need to subtract the components, V minus U, which is X1 minus X2, Y1 minus Y2, and Z1 minus Z2. Of course, if you have scalar or a fixed number or a scalar like C, you can define a new object C times V, which is C times X1, Y1, Z1. So in some sense, we just distribute this scalar or number into the components of this vector. Cx1, comma, Cx2, Y1, and comma, Cz1. So we're actually forming a new vector. And also know that if C is equal to -1, we get the opposite of our vector. So minus V is minus X1, minus Y1, and minus Z1 in the opposite direction of vector V. So if you have vector V here, its opposite, minus V, in the opposite direction is minus V. Now some new operations between these two vectors. We can define two products for two vectors in three-dimensional space. The first is called the dot product, inner product, or dot product. So the inner product of two vectors always is one number. So the result is a constant. We define it this way: U times V or V times U, V dot U. You multiply the first components, the second components, the third components, and add them all together. X1 times X2 plus Y1 times Y2 plus Z1 times Z2. You have numbers, you multiply these numbers together, add them all together. The outcome of dot product or inner product between two vectors is always one number. Note that You can also define the dot product this way. The dot product between V and U can be defined as the magnitude of V times the magnitude of U times cosine theta. What is theta? Theta is the angle between V and U. Here for you. This is your V, this is your U, and this is theta. If theta is given, we can use it to find the dot product between two vectors. Before going over any example about dot product, I'm going to define cross product as well for you. Cross product. So you see the difference between these two. The result of a cross product is always a vector. The result is a vector. Okay. We define cross product between, for example, three vectors, two vectors V and U, V cross U, to be the determinant. The first row of your determinant is standard vectors. We defined them last lecture, I, J, and K. Remember, I is 1, 0, 0, J, 0, 1, 0, and K is 0, 0, 1. And on the second row, you copy down the components of the first vector. X1, Y1, Z1. On the last row, you copy down the components of the last vector, U. So X2, Y2, and Z2. There you go. So how do we find the determinant? This is I times Y1, Z2 minus Z1, Y2 minus J, X1, Z2 minus Z1, X2. And finally, plus K in the direction of Z axis, X1, Y2 minus X2, Y1. There you go. Let's go over some examples, see what's going on here, how to find the dot product, how to find the cross product between two vectors. So suppose you have this example here. You have two vectors. You have vector A, which is defined as 2, 2, negative 1, 2, 2, negative 1, and the second vector is defined as 5, negative 3, and 2. Question says, first of all, find the dot product between these two, then you're going to find the cross product as well. What is A dot B? What is A cross B? Okay. A dot B, the inner product between them is easy. Inner product. Okay, perfect. So we have 2 times 5. 2 times 5 plus 2 times negative 3, 2 times negative 3 plus negative 1 times 2 times 2 Then we do the multiplication and we add them all together. This is equal to 10 minus 6 minus 2, 10 minus 8, which is 2. The inner product or dot product between these two vectors. Now for the cross product. You have I, you have j, and you have k. The very first row shows the direction in the direction of x-axis, in the direction of y-axis, and in the direction of z-axis. We copy down the first vector a, 2, 2, minus 1. We copy down the last vector 5, negative 3, 2. This guy gives you I, 2 times 2, 2 times 2, minus negative 1 times negative 3, minus j, 2 times 2, 2 times 2, minus negative 1 times 5, plus k in the direction of z-axis, 2 times negative 3, minus 2 times 5. Okay, so here you have I, 4, minus 3, minus j, 4, plus 5, and finally you have k. They have negative 6, minus 10. So your vector is 4 minus 3 is 1, so the first component is 1, the second component is negative 9, and the last component is negative 16. This is the cross product, and this is the dot product. The dot product or inner product is always a constant in number, and the cross product is always a vector. This vector is perpendicular, or we say orthogonal to the plane including these two vectors. So let us graph these vectors. So the second one is 5, negative 3, and 2. 5, negative 3, and 2. Okay. So let us use a different color for this, red. And for this guy, let us use purple. And let us add their cross product. Let me use green. Here you have 1, negative 9, and negative 16. 1, negative 9, and negative 16. Very well. Let me just rotate this a little bit for you. Stop here. So if you consider the plane including red and purple vectors, if you consider the plane including these two, the green vector, which is the cross product, is orthogonal or perpendicular to this plane. Okay, let's see what do we have. So that was the difference between dot product, cross product, more on dot product. So in this example, we have an example. This example says, find the angle between these two vectors. The first vector is defined as 2, 2, negative 1, the same vectors that we have, and the vector b for negative 3 and 2. Okay? Our goal is to find the angle. We just learned about the formula, the dot product formula, including theta or the angle between two vectors. You know that A dot B can be written as the magnitude of first vector times the magnitude of the second vector times cosine theta. So you can rewrite cosine theta as A dot B divided by the magnitude of A and the magnitude of B. Then theta is equal to inverse cosine of A dot B divided by the magnitude of A times the magnitude of B. There you go. So what do we need? We need A dot B, the dot product. We also need the magnitude of A. Remember that to find the magnitude, it is the square root of the first component squared plus the second component raised to the second power plus the last component raised to the second power. We also need the magnitude of B. The first component raised to the second power, the second component raised to the second power, and the last component raised to the second power. You need to find all of these, then plug them into the formula. So we already calculated the dot product. We know that the dot product is equal to 2. Now let us find the magnitude of these two vectors. Vector
Excuse
A.
me. Is it inverse cosine equal?
Okay, magnitude of A is equal to square root of 2 squared, 4, 2 squared, 4, negative 1 squared, 1. So you get square root of 9, which is 3. Now for magnitude of B is equal to square root of. So the first component raised to the second power, 25, plus 9, plus 2 squared, which is 4. There you go. The magnitude of B is equal to square root of. Here you have 13. You get 30. Square root of 30. Okay, let us get back to the formula. The inverse cosine of A dot B, the dot product, is 2 divided by 3 times square root of 38. This is equal to theta. For this calculation, you have to use your calculator. If you use your calculator, theta is equal to 1.46. 1.46 or 80, let's see, 84 degrees. There you go. Let's see what do we have here. Okay. We are on page 4. Good. So we learned that the dot product or inner product between two vectors can be written as the magnitude of the first vector times the magnitude of the second vector times the cosine theta, the angle between them. So I expect you to ask, what if theta is equal to 0? What if theta is equal to pi over 2? If theta is equal to 0, then cosine theta or cosine of 0 is equal to 1. A dot B is the magnitude of A times magnitude of B. If the angle in between is pi over 2, cosine of pi over 2 is equal to 0. The dot product between A and B is going to be 0. Think about it this way. The angle between them is pi over 2. So this is your first vector, like I, 1, 0, 0. And this is your second vector, j, which is 0, 1, and 0. So if you form the dot product between these two, I dot j, 1 times 0, 0. 0 times 1, 0. 0 times 0, 0. The dot product or inner product is always 0. And the angle between them is pi over 2. So in general, you can say that two vectors, no, two vectors, like A and B, are orthogonal or perpendicular if and only if their dot product or inner product is equal to 0. Very well. Let's define direction angles. Definition. Direction angles. So when you have a vector like A, that vector forms different angles with x-axis, with y-axis, and with z-axis. For vector A, we can define direction angles which are angles between A, vector A, and x-axis, also y-axis, also z-axis. We define it this way. For vector A, suppose you have components A, B, C. The angle between A and x-axis, let's call it alpha. Cosine alpha is going to be A divided by the magnitude of vector A. Cosine of beta. Beta is the angle that A, vector A, forms with positive side of y-axis. So this is second component, B divided by magnitude of vector. And cosine gamma, which is equal to C divided by magnitude of the vector. So alpha, angle with x-axis, beta, angle with y-axis, and gamma, the angle with z-axis. These are called direction angles. Very well, let's continue. Scalar projection of one vector over another vector. Let's go over the definition first, then example. So definition. Let A and B be two vectors. We can project vector B onto vector A. So that makes sense. You have two vectors. Suppose this is your vector A, and this is vector B. You can, of course, project vector B onto vector A. You get a new vector. There you go. So the scalar projection of B onto A follows the formula A dot B, the dot product between these two vectors, divided by the magnitude of vector. This is scalar projection, and note that on the numerator you have a constant, you have a number. On the denominator you have another constant, another number. The outcome is a number. Number divided by number. This is not a vector. To get a vector, we say, okay, the vector projection of B onto A is defined this way. The dot product, so you take a scalar projection and you multiply it by unit vector A over the magnitude of so this is just the multiplication. So this is a scalar, this is a number. This is a vector. So the outcome, the total outcome is going to be just a vector. This vector here. So let us rewrite this formula here for you. We don't want to lose these. A dot B over the magnitude of A. The scalar projection so we have an example. Example gives you two vectors. Let vector B be equals to 1, 1, 2. And vector A is given as negative 2, 3, 1. And the question says, find the vector and scalar projection of B on A. Find the scalar and vector projection of B onto A. Okay, what do we need? We need the dot product between A and B. We need the magnitude of vector A. So A dot B. The dot product, the inner product, 2 times negative, 1 times negative 2, minus 2, plus 3, plus 2, which is equal to 3. Now let us find the magnitude of vector A. The magnitude of vector A is equal to square root of 4 plus 9 plus 1, which is equal to square root of 14. So we have all the information we need. This is equal to 3 over square root of 14. Of course, you can rationalize this by multiplying by square root of 14 divided by square root of 14. So the scalar projection is 3 times square root of 14 over 14. Now for the vector projection, you already found the scalar projection. So this is equal to 3 times square root of 14 over 14 times vector A, which is 2, -2, 3, and 1, divided by the magnitude of vector A, which is equal to square root of 14. So here you can just cancel out these two radicals and start distributing 3 over 14 into the vector components. So here you have -6 divided by 14. We could simplify this, -3 divided by 7, comma. So you have 9 over 14, and finally you have 3 over 14. More on cross products. Okay. So let's go over one example together. Suppose I give you just one vector. Let A be a vector with components a sub 1, a sub 2, a sub 3. Here's two questions for you. What is A cross A? What is A dot A? Cross product, dot product, or inner product? Okay, very well. For cross product, we have to form the determinant. So this is equal to the determinant I, J, K, A sub 1, A sub 2, A sub 3. Since A and A are the same, we're going to repeat these components on the last line as well. A sub 1, A sub 2, A sub 3. Okay, now let us calculate this determinant. I, A2, A3, minus A2, A3, minus J, A1, A3, minus A3, A1, plus K, A1, A2, minus A2, A1. Very well. What do we have here? We have vector. Guys, this is a vector. 0, 0, 0. This is vector 0. That makes sense. What do you have here? You have vector A, and you're finding a vector that is perpendicular to the cross product of these two vectors. But what is the cross product of these two vectors? The cross product of these two vectors, as you can see, is equal to 0, 0, 0. So how do you find a vector that is perpendicular to the plane, including 0, 0, 0? It's just going to be 0, vector 0 itself. What about the dot product? The dot product is going to be like this. A1 times A1, A1 squared, plus A2 squared, plus A3 squared. But remember that when you have A1 squared, A2 squared, A3 squared, this guy is equal to magnitude of A raised to the second power. So the dot product between A and A has nothing except for the magnitude of A raised to the second power. New formula for you. Okay, one note for you. Note that we already learned that if you have two vectors, the dot product between these two vectors can be written as the magnitude of the first vector times the magnitude of the second vector times cosine theta. We know that the cross product between two vectors is a vector. So what's the meaning of that? It means that you can find the magnitude or length or norm of this vector. So you can find the norm or length of the cross product between A and B, which is denoted by A cross B. The magnitude of the cross product between two vectors is the magnitude of first vector times the magnitude of second vector times sine theta. Theta is the angle between A and B. Very well. So where do we use the cross product between two vectors? Another note for you. Note that we eventually use the cross product of two vectors to form equation of a plane. So let's go over one example together. Example. This example says you have the following vectors and 1 point. It says find a vector perpendicular to the plane that passes through two vectors. Actually, it gives you points, so we can form the vectors. Passes through 3 points. So the first point, T, is 1, 4, 6. The second point, Q, -2, 5, and -1. And the last point, R, is 1, -1, and 1. Okay, there you go. So what do we have here? We have a plane with these points located in that point. P, for example, is here, Q is here, and R is here. 3 points in that point. We want to find a vector which is perpendicular to this plane passing through these points. Right. So we know that cross product of two vectors is perpendicular or orthogonal to the vectors, and also the plane including those vectors. So what I'm going to do, I'm going to take these points and form two vectors. We use these points to form vectors. So, for example, let us form the vectors PQ and PR. PQ and PR. Remember that to form vector, we write the components of the second point first. So it's going to be like this: Q, -2, -1, comma, 5 minus 4, comma, -1 -6. So this vector and the second vector, PR. PR. So the second components are, comes first. You have 1 minus 1, comma, -1 minus 4, comma, 1 minus 6. Let's form these two vectors. The first one is equal to -3, 1, and -6. The second vector is 0, -5, and 1. Well, you have two vectors. Now you can find the cross product between them, and there you have your vector. PQ cross P. You have I, J, K, PQ, -3, 1, -7, PR, 0, -5, and 5. There you go. What do we have? We have I, 1 times 5, 5 minus 35, minus J, -15, minus 0, plus K, which is 15. So this is your vector. -30, +15, and 15. I make a mistake here. Let me double check. Okay, this is -5. Let's fix that. 1 minus 6 is -5 now. Okay. So here you have -5. So here you have negative. So you get -4. Let's fix this one here. And I use this. Okay. And for my J, so I have +15. So I have -15 here. And for my K, I haven't used it. Okay, perfect. There we go. Another formula for you. So suppose you have 3 vectors. Okay, let me find it. No, suppose you have vector A, then you have vector B, and here you have vector C. So suppose you form a 3-dimensional object here. So let's see. Put this one here, horizontal axis. Okay. And there we go. Suppose you have a 3-dimensional object. The volume of this 3-dimensional object is actually the magnitude of A dot product with B cross So B cross C, the magnitude of B cross C is actually the area down here. The magnitude of B cross C is the area of the base. What is your base? Base is just right there. This is B, and this is C. Again, don't forget it's the magnitude. Otherwise, if you just form this as B cross C, it's just a vector. But if you find the magnitude, it's going to be the area of this two-dimensional object down here. And to find the volume, we need to find A dot B cross C. Sometimes you can write it this way. The determinant of A1, A2, A3, B1, B2, B3, C1, C2, C3. Well, let's go over one example together. Example says, find the volume of the object formed by these vectors. So the first vector A is 1, 4, negative 7. B is 2, negative 1, 4. And C is equal to 0, negative 9, and 18. There you go. The volume follows the determinant of the first vector, 1, 4, negative 7, 2, negative 1, 4, and the last vector, 0, negative 9, and 18. If I factor out 9, let's write it this way. So you have 1 times negative 18 plus 36 minus 4 times 36 minus 0 plus minus 7 times negative 18. Very well. Let's do the algebra. You get 18 minus 4 times 36. So let us name it as 18. And I have, okay, I have positive number. That's a good thing. 144, and I have plus 126. So if you add these two together, you get positive 144. The outcome is equal to 0. It says volume is equal to 0. Let's graph it together, see what's going on. So the first vector 1, 4, negative 7. The second vector is 2, negative 1, 4. And your last vector is 0, negative 9, and 18. X, Y, Z. As you can see, there is no three-dimensional object formed by these three vectors. So you expect to get a zero volume. That's the reason behind it.